Hi, everybody, and welcome to this session. This is going to focus mainly on homework, basically assignment. That's really the whole point of it. There's a homework that you guys have before you. And there's another homework that is coming. Actually, you'll have two more homework coming down the road and immediately, I think, next week. So the focus is on that. There was a question that was some of you asked, the ones who are sitting in the lab, basically not the ones who are not doing lab, about the lab, for example, if in case you have COVID, and what happened in that case. I need some sort of a doctor's note or something to support your situation, because we really don't want to spread anything in the community, in the classroom. But then in this case, you're not completely off the hook, because you'll have to check with somebody. And if you can't find somebody, please let me know. I'll try to arrange with somebody to share their data and then their observations so that you can at least continue your work. Because here is the thing, emergencies do happen. And when they do, we really don't want them to be in the way, basically, of finishing what we're supposed to be finished. Because at some point, if you're missing a lot, then what's the point? Basically, it's much better actually to restart the class some other time. So that's the point I'm trying to make in here. So if in a situation where you really cannot come, especially if you have something that is as dangerous as Corona is, still is, then in this case, of course, you cannot come, you should not come. But then in this case, we will try to arrange for you to still do your work, if provided, of course, you can do it. Okay. So that's in a nutshell to follow up on somebody's else question. Okay. Obviously, if you have specific unique circumstances, you really need to discuss them with me, send me a private message, and we'll be more than happy to answer them along those lines. Okay. So this is for those who are in the lab class. And those who were not in the lab class, you still are also, I mean, for those who were taking the physics one, I mean, Astronomy 120 only, then in this case also, you might have some emergencies that prevent you from basically doing what you're supposed to be doing. In that situation also, while the emergency is happening, yes, you're granted some sort of a time, but at the end, you really need to complete your task. You need to do your stuff and complete your task in a timely fashion, okay? Otherwise, again, it becomes a little bit to answer your question, David, you need to be enrolled in Astronomy 125. That's the lab for Astronomy 120. Okay. If you're not in that class, then ignore anything I said about Astronomy 125 and the lab section of it. Okay. There was also another question, and I know it does not apply to you guys because we're already in session. There is a late class session that are starting next week. And they were wondering, I mean, about the difference between 120 and 125. Do they have to take 125 if they do have to take 120? That is an answer to David also. No, you don't. But the other way around is true. You cannot take 125 if you did not take 120, or you're taking it at the same time. So that's basically the whole thing in here. Which brings me to another important point. Starting from next week, the late sessions start, and the late sessions are I have a lot of them, actually. More than half of my classes are going to be late start. So in other words, there might be some delays in terms of those recordings and how they are posted on Canvas. So you really have to, it's a good idea to subscribe to the YouTube channel. If you don't know the link, just basically go to YouTube. And I can actually provide you the link sometime. I think I probably should do it now because I have access to it. So just put DJ Bouzidi. That's my the first two letters of my name, and then and my last name. Okay, and you should be able to find it. So again, here is the. Let me get into the link if I can get the link. There is the link. Let me remove this thing in here. I don't know what that playtest means. It's a good idea to subscribe to it just to avoid the delays, or at least some sort of to jump right away on it. That's number one. Number two, also that you should be aware of, all of my postings on that channel will have the first name as your class. So if you see something other than Astronomy 120-70, that's probably not your class. I mean, there is another one that looks very much like it, Astronomy-71, I mean 120-71. That is actually the late start session. So that is not your class, okay? Astronomy 125, I don't know if we do recordings for it, but if it does, it will have its name. There is another Physics 101 or 100. That is another one that is completely separate, at least in this semester. There is another class that I'm doing, but that's not going to be having YouTube channels at this point, and that is Physics 202. Anyway, the point being in here is it's a good idea to subscribe to those things, at least to get some of the resources quickly for your class, especially when we are having more classes nowadays. Okay. Let me share with you the screen so that we understand what we're doing today. I want to talk about two things. First of all, the format, and second, the actual questions and how best to answer them, okay? And there is a lot of work, okay, so that you guys know. So let me share with you. Not that. Let me open, first of all, the proper window for it, and then share. No, not the inbox. I don't want the inbox. Share. Okay. So this is something that you have seen. I can actually go to the student review if I want to. And this is exactly the assignment that you have seen from this week. Okay. It has 30 possible points. And 30 possible points in here for this questions. You have 12 and 18, basically. You have 4 points times 3 to answer this 3 questions. That's 12 points. And you have these 2 questions, each and every one of them is worth 9 points for a total of 30 points. So that is basically in a nutshell. I know we did this and we did it extensively. So it's a good idea to go back and review that resource that we did. Does anybody remember? I think it was not, it was last Thursday, wasn't it? When we did this in an extensive discussion. Okay, very good. Thank you, David. So it was Thursday, August to the 25th, when we did this one, and we did it extensively. It was toward the end. So if you go back into Canvas, for example, and you look at the modules, and you see the recordings, and we did it in extensive, basically, research there. So it's a good idea to summarize it and put it in your own words, okay? So that you can have that done. And I believe also we did this one too on the same day, but we didn't do it as much as in detail. Basically, what those 2 tables are, and again, in the problem from the book, tells you to refer to appendix tables 1 and 7. And I actually included tables 1 and 7 for you guys in here so that you can do this. And again, I think we did them in summary. Again, if you're having difficulty with it, please let me know. From table 1, here is table 1, you will have, among other things, because you will need the size of the moon, the size of the sun, the distance to the moon, and the distance to the sun. And you're supposed to find the ratio of those sizes to those distances, and you're supposed to find the same number. And hence, you argue that that's why there is a lunar eclipse that covers the entire sun, okay? Because the sun intervenes between the Earth and the sun, and it is just that right size and at that right distance to cover the entire sun, so that we can barely see the corona of the sun during a solar eclipse. So again, table 1 gives you a bunch of information: the velocity of light, gravitational constant, Planck's constant, mass of hydrogen. Most of these things, we don't need them in this class, but sometimes we might need something. Mass of an electron, Stefan Boltzmann constant, Wien's law constant, and then astronomical unit, you need this number. You need the astronomical unit because that's the distance from the Earth to the sun. And it's given to you in meters. It's very important to know what the units are. And here it's telling 1.4959, whatever that whole thing in there. times 10 to the power 11 meters. Approximately, and you're not too far off, you could say it's 1.5, 10 to the power 11 meters. So that is one thing. The other thing also that is given in this table, light in years, parsec, year, mass of the sun, we don't care for it. Radius of the sun, we need that. It's telling us it's 6.96 times 10 to the power 8 meters. So we need this information, okay? And then the luminosity of the sun, we don't need it yet, at least for this problem. And Hubble's constant, we don't need it yet. We need it for some other number, for some other classes. Okay. Then on table 7, it's giving me a bunch of information about the moons, actually, of all the different moons that we know of. Today, we know more than 200 moons, but you're not listed 200 moons in here, just the big moons. Earth's moon, it gives you the radius, 1,738 what? Kilometers. Here, it gave you the radius of the sun as 6.96 times 10 to the power 8 meters. There is a discrepancy in here in the units. I cannot compare apples to oranges. I really have to compare apples to apples. So this one is in meters for the radius of the sun. This one is in kilometers for the radius of the moon. So one has to go to the other. Either multiply this one by 1,000 to make it in meters, and the number would be 1,738,000 meters, or make this one in kilometers by dividing it by 1,000. The number then would be 6.96 times 10 to the power 8 divided by 10 to the power 3. That should give me 10 to the power 5. So one of the two has to happen. Either change this one to meters or change this one to kilometers. Okay. Then also what is given to us in here is the distance to the moon. The distance to the moon is 384.4 thousand kilometers, not kilometers. It's 10 to the power 3 kilometers. So in other words, 384,400 kilometers. So the units in here matter. The distance to the sun, which is the astronomical unit, is 1.495978706. That is with that much precision. That's just to tell you how much we know the distance to the sun. We don't need it to be that precise, though. 1.5 will do. Times 10 to the power 11 meters. Again, we're suffering from the same problem. This one is in meters. This one is in thousands of kilometers. So we must use the same number of units so that we compare apples to apples and not apples to oranges. Okay. Let me share with you another screen because probably some of you do not, because a lot of you probably are not too familiar with the power, how to do conversions and things like that. So I want to make sure that we're all on the same page. So let me share this one in here, because in here I can take, how do you convert? First of all, remember, I need to change the color of this pen. Change the thickness also. Okay, so 1 kilometer is 1,000 meters. Okay, that is basically, oh, I'm sorry, I'm not sharing my screen. Sorry about that. Okay, anyway. So 1 kilometer is 1,000 meters. That's basically what the K stands for in here. Another thing that you might encounter, 1 mega, for example, meters, or 1 mega something, 1 megaton, 1 mega, whatever number that is appended to it. Mega is actually 1,000,000. Meters. 1 giga, which is another thing that you might encounter somewhere, gigawatts, for example, I'm sorry, or giga something, gigahertz. For your phone, for example, operates at the frequency of 2.4 or 5 gigahertz, 5 gigahertz. So what that is saying is 1 billion hertz, that's all, okay? 1 gigameters is a billion meters. That's what the giga stands for. Okay. So again, we're sick and tired of writing those so many zeros. That is not a shorthand writing of things. So people use the power. So 1,000 in this case is how many zeros? There are 3 zeros. So I write 10 to the power 3. Why? Because if I take 10 times 10 times 10, 10 times 10 is 100, times 10 is 1,000. And that's what the power 3 means. Means that take 10 and multiply it by itself 3 times. Okay, so meters. Same thing in here. 10, how many times do I have to multiply 10 to get a million? 6 times. 10 times 10 times 10 times 10 times 10 times 10. I get a million. Okay, same thing in here. Billion is 10 multiplied by itself. 10 times 10. 10 times 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 10. 9 times, okay, to get a billion, and so on and so forth. Okay, those are most of the numbers that we will be dealing with in this class. On the opposite side of this thing in here, you have the milli. This is a millimeter. A millimeter is 1,000th of a meter. Take a ruler, a meter long, and you divide it into 1,000 pieces. One of those pieces is a millimeter. Okay. A centimeter, though, which is slightly bigger, take a ruler that is 1 meter long and you divide it into 100 pieces. Each one of them is a centimeter. In other words, a millimeter is 1/10 of a centimeter. Okay. There is something even less than a millimeter, which is called a micrometer. The Greek letter mu, the Greek letter mu is used in this case. So what is a micrometer is a millionth of a meter. It's very small compared to the, and this we will need it for a frequency, for a wavelength. Wavelength, for example, of the red color is about 700 micrometers. So the symbol for it is, I'm sorry, nanometers. Something wrong. It's 0.7 micrometers. Okay. We will need it actually for the infrared. Remember how James Webb telescope right now is operating? It's operating actually is within this range, few micrometers left and right. Okay. So for the visible light, the red that I was going to use actually is used in a nanometer. The number I put in here is correct, by the way, but the nanometer is a billionth of a meter. That is the same number, 0.7 micrometer is actually 700 nanometer. This is the red color. Okay, something smaller than that, about 400 nanometers or 450 nanometers is actually the blue color. Blue probably should be more like 500. Okay, 450 is more like the violet. It's really highly different. But the point being in here is that those are the numbers that we're going to be using. So sometimes you see these short numbers next to the problems. Pay attention to what this means. Okay, again, in a similar fashion, 1,000th is you take a number and you divide it by itself 1,000 times. So 1 and divided by 1,000 times. That's what this number means exactly. Okay, thousandths of a meter. And a thousandths of a meter, I remember 1,000 itself is 10 to the power 3. So this can be written as 1 over 10 to the power 3 meters. Or in the same fashion, take 10, let me move this out of the way, 10 to the negative 3 meters, as opposed to 10 to the power 3 meters. Okay. So that is same thing in here. It's going to be 10 to the negative 6 meters, and this one is going to be 10 to the negative 9 meters. So this is something called actually the scientific representation. And the scientific representation of numbers, you append a power to any number plus a digit in here between 1 and 9, including 9. So times 10 to the power something in here. It could be positive or negative. So this is part of the stuff that you probably should have seen or have seen somewhere else. If you didn't, this is an introduction to it. So let me go back into those tables in here just to show you. So let me stop sharing and show you what that means, all of this representation, at least in the problem. Share. The entire table in here, the first table, 1, is actually in scientific notation. Scientific representation, I should say. The speed of light is 2.9997, whatever that number. This number must be more than 1. I mean, it could be 1 or more, but 9 or less. I mean, 10 or less, I should say. It cannot, not 10, less than 10. It could be 9.9 if you like, but it cannot be 10. You cannot put 11 in here, or 12 in here, or 27 in there, or 324 in there. That is not acceptable. The number has to be between 1 at least, and anything just less than 10. It cannot be 10. 9.9999 is fine. Okay, that is one thing. And then times a power of 10. In this case, 8 to the power 8. In this case, to the negative 11. So what I have in here for my case, I have 1.495. That's basically the speed of the distance from the Earth to the Sun times 10 to the power 11. So what that means is it's 1.49 times 10 to this many numbers, which turn out to be, remember, a billion is 10 to the power 9. This is 100 times bigger than a billion. This is 149 billion meters, or 149 million kilometers. That's the distance to the moon, to the sun, from the Earth. On the same token, the radius of the sun is 6.96 times 10 to the power 8 meters. That means remember 10 to the power 6 is a million, but this is 100 times bigger. As a matter of fact, 696 million meters. If I don't care about the meters and I want it in kilometers, it's going to be 696,000 kilometers. That's how big the sun is. So we need to understand how to convert it, to read these numbers really. Here, it's the first, at least for the moon, all of these representations are not in a scientific representation. 1,738 is more than 10. Remember, it cannot be more than 10. So technically, if I want to write it in scientific notation, I will write this one as 1.738. Then count how many numbers I had to put out behind the decimal point. I had to put 1, 2, and 3, which is 10 to the power 3. So technically, this answer should be 1.738 times 10 to the power 3 kilometers, if I want to make it in a scientific representation. This is not a scientific representation, nor this number is. None of this numbers is, except the last one in here, it's fine. Okay? This one is actually in scientific notation. You don't see the 10 in here because it assumes to be to the power 0. Anytime 10 to the power 0, that's 1 actually. So this last one is okay. This last two are okay. But this one in here is not. This one is not. So none of this table in here seem to be at least in scientific notation. Okay? But this one is. So we really have to make sure when we're reading the data, we understand what we're doing, what we're reading. So to answer the question to that problem, it gave us the distance to the moon as 1.495, I mean the distance to the sun, times 10 to the power 11 meters. This is Earth, Sun distance. The distance to the Earth and Moon is given 1,738 kilometers. As I was saying in here, this units need to match. One way of doing it is multiply. Remember, a kilometer is 1,000 meters. So I can convert kilometer by just making it into 1,000, and we're done. That's good. So all I have to do is write this one, 1,738,000. That's what, or 10 to the power 3, which is the same thing, meters. So now I don't have the kilometer because I replaced it by its value, which is 10 to the power 3 meters. So we're good as far as this part. Same thing. The radius of the sun is 6.96 times 10 to the power 8 meters. But the radius of the moon, oh, did I put it backward? They probably put it backward. I'm sorry, this is not the distance. This is the radius of the moon. Where is it? Delete it in here. This is the radius of the moon. I'm sorry. The distance the Earth to the moon is here. This is the radius of the moon, not the radius of the sun. Radius of the moon. And this is the radius of the sun. I'm sorry about that. Okay, I need to go back into the table to make sure I'm copying the numbers correctly. So the distance to the moon is 384.4 thousand kilometers. So the Earth-Moon distance is 384.4. In parentheses, if you look at the table, it says 1,000 kilometers. Again, I need to convert this to the same thing by multiplying it by 1,000 to bring it back to everything in the same units, so that my comparison can be justified. In other words, 1 kilometer is 10 to the power 3 meters. So I have to bring another 10 to the power 3 in addition to the one that is in the table. Okay, so this will become 384.4 times the 10 to the power 3 that is part of the table times another 10 to the power 3 that is part of the conversion into meters. Now I have the Earth moon radius, distance. I have the radius of the sun, radius of the moon, and the Earth sun distance. Okay. One way of doing it is actually taking this ratio of the Earth to the sun divided by the Earth to the moon and comparing it with the radius of the sun divided by the radius of the moon. Now, one thing you really need to know when you're doing divisions, because they involve all of these powers in here. You have 10 to the power 3, you have 10 to the power 11, you have 10 to the power 8, and now you have two of them, 10 to the power 3 and 10 to the power 3. So we really need to do these things in here. An easier way of doing this one is just punching these numbers on a calculator, and that should work too. However, you should know that when you multiply powers, you add them. So this is the same thing as adding 3 and 3. That's it. So this is 10 to the power 6. So this number in here is the same thing as 10 to the power 6. Why? Because 10 to the power 6 is 1,000, and 10 to the power 6 is 1,000. And when I multiply 1,000 by 1,000, I get 10 to the power 6, which is 1,000,000. This is exactly what I was doing earlier in here. Remember, 1,000,000 is 10 to the power 6, which is 10 to the power 3 and 10 to the power 3. So the powers are really counting how many zeros you have. You have 3 zeros in 1,000, and you have 6 zeros in 1,000,000. So all of this should be able to get you to this number. So we solved that problem. Now the division, because at some point I'm going to take the ratio of the Earth sun divided by the Earth moon. The Earth sun distance divided by the Earth moon distance. Let me write it down explicitly. The Earth to the sun is 1.495 times 10 to the power 11 meters. The Earth to the moon distance is 384.4 times 10 to the power 6 millionth meters. I'm sorry, 384.4 times 10 to the power 6 meters. Okay, see the wisdom of making the conversions? Now I can cancel this meter and this meter, because now I'm comparing apples to apple. You see, now I'm getting a number that doesn't have any ratio in it in units at all. I'm getting a dimensionless number, a number that does not have units. It's just a fixed number. So now it's just a matter of doing the division, okay? In the same token, let me just write the ratio of this radii, radius of the sun over the radius of the moon. So the radius of the sun over the radius of the moon is 6.96 times 10 to the power 8 meters, divided by the radius of the moon is 1,738 kilometers. Remember, I multiplied by 1,000 to bring it to a meter. So it's going to be 1,738 times 10 to the power 3 meters. Again, now I can cancel a meter and a meter. That was the wisdom behind the conversions. Otherwise, I cannot do this cancellation. Kilometer does not cancel a meter. I have to convert one or the other to do this cancellation. Which brings me to the last point in here before punching things in a calculator. I have this 10 to the power 11 and I have this 10 to the power 6. And I have also 10 to the power 8 and 10 to the power 3. In algebra, they tell you if you divide a power by another power, you subtract the powers. The one in the numerator stays positive and the one in the denominator becomes negative. So basically, it's the same thing as saying 10 to the power 11 minus 6, which is 10 to the power 5, by the way. Okay. And the same thing in here, 10 to the power 8 divided by 10 to the power 3. That is the same thing as 10 to the, again, 8 retains its sign. It was positive, it stays positive. And the one in the denominator changes sign and becomes negative 3. And that too is 10 to the power 5. Okay. Now it's just a matter of playing with the other numbers. It's just a matter of finding 1.495 divided by 384.4 and dividing 6.96 divided by 1,738. There is a danger in here, and I will tell you what it is for both of these numbers. Let me just do the first one as an example, and you will see exactly what I'm talking about. I have 1.495, and I want to divide it by 384.4 because I already did the powers. It's 10 to the power 5. So multiplied by 10 to the power 5. So it's this ratio I'm writing in here. Because the denominator is a lot smaller than the numerator in the first fraction, I have an issue, and I will tell you what it is. So I'm going to pull the calculator right now. So let me stop sharing this screen in here and see what kind of calculator I have on this computer. Do we have Mathematica? Mathematics? No, I don't. Do I have any calculator in here? Calculator. Okay, I have a calculator. So I'm going to share. Oh, shit. What happened here? Calculator. I'm going to share the calculator. It doesn't matter how fancy the calculator is. So I'm going to share the calculator so that you see how the calculation is done. So it says, let me look at it again. 1.495. 1.495 divided by, and when I make the division, I'm making it divided by 384.4 and hit enter. So it's giving me this tiny number, 0.003889177. I mean, I have to be careful. I rounded the distance so within at least 3 digits. I cannot really retain more than that. So I cannot really say all the way to 0.462. That is not correct, okay? But the point I'm saying in here is I have to multiply it by that 10 to the power 5. And 10 to the power 5 is 10 times itself 5 times. 10 times 10 times 10 times 10 times 10, which is 100,000. So I really have to multiply it by 100,000. So a lot of those decimal points in here will disappear. And the answer should be about 400 or 389. Okay, so let me do that. Let me multiply it by 10. Do I have in here a power? I can probably change it to from standard to a scientific. And now I lost all of the calculations. Sorry about that. So let me do it again. Okay, sorry. So again, we have 1.495 divided by 384.4. And this is the answer. Now we have to multiply this number by 10 to the power 10. No. Okay, sorry about that. Let me divide it by Okay, this is the answer if you did it correctly, okay? If you missed the last step, I multiplied it by mistake by 10 to the power 10, then it divided by 10 to the power 5, it gave me the same answer, okay? If you're confused about this one, please let me know right away of what happened. Basically, if you did it on your own, you divide the number, you might be tempted to find a very tiny number, and that's correct, okay? Because 1.495 divided by 384 is a very small number, but don't forget you're multiplying it by 100,000. Okay, that's going to make up for that difference, discrepancy. Just for comparison's sake, so this is 388.911. Again, I should really retain only about 3 significants. In this case, it's going to be 389, roughly about 400. The ratio of the distance to the sun over the distance to the moon is about 400. That's basically a very easy and round number to remember. Instead of having to remember 388.900, because it's very close from 400. Okay, so let me do the same thing for the other one, which is 6.96 divided by 1,738. Okay, 6.96 divided by 1,738, and that is a very tiny number, okay? Again, I'm going to multiply it by 100,000, which is 10000. That's 100,000, which is 10 to the power 5. Okay, I could have written 5 and then hit it with the number 10. It's going to do the same thing. So the answer is about 400. That's the whole point. Actually, the ratio of that distance is entirely smaller, but it's insignificant. Okay, so that's in a nutshell the answer to the whole problem. Okay, so does this make sense to you? For those who are not too, they didn't take a lot of algebra, does this make sense? For those who took a lot of algebra, this is probably kind of too easy for them. Okay. That should help you at least with this homework assignment. The other 3 questions, I think they're straightforward. Let me share with you the stop. No, I'm not sharing anything. So let me just share. So this part in here, what is the phase of the moon during a total solar eclipse? When the sun is completely covered. Anybody knows the answer to this one without having to go and look at the book? Very good, David. That's the correct answer. When it's a new moon. When it's during a total solar lunar eclipse. The second part. So the solar eclipse, we know it's a new moon. How about when it's a lunar eclipse, total lunar eclipse? Okay, very good. Thank you, Susan. So that's really answers that part. Okay. And then why don't we have lunar and solar eclipses every month? And that is part of the discussion that a lot of you have answered. But again, that should be also something. Why does the moon look red during a total solar eclipse? And that has to do with how the rays basically of the sun hitting the atmosphere of the earth get deviated to the moon. Okay, so this is basically in a nutshell your homework. Okay, let me stop sharing and share with you another one in here. Let me first of all leave the student view. And this is homework number 2, actually. Okay, share. I cannot do it in student view, this one, because of the fact that it's still not published, because it's going to be ready this weekend. But this is actually another homework that is actually based on unit 10 that we just covered this week, okay? This is from, it's going to be due in probably about 10 days from here. But the idea in here is that before I do that, let me talk about something else. I'm sorry, okay? I need to regress a little bit. The reason why I'm saying that is because it's very important that we cover all the details, at least the mechanics of how these things work. So let me go back into homework 1 in here. And let me go back into the student review. Now you're ready to submit stuff. For those who took already this class, I mean, online classes before, this is no big deal. So you can come in here and you know exactly what to do. You can do a text or you can do an upload. So if I do a text upload, it's a good idea to answer specifically the questions in here, question 1 from part 1, and then answer. So I've tried this in here. Oops. So I'm going to go question 1. Part, the numbers are not working now. Question 1, part 1. And then put the answer to it. And the same thing in here, I'm going to go to question 2, part 2, and then answer it. I cannot really jump the questions. I cannot do 3, for example, question 3. Please be more verbose than what I'm doing right now. But the point being in here is I need to stay in order. I should not really put things, oh, I will come back to question 2, therefore I'm going to do question 3. Question 3. Part 1, this is still part 1, okay? This is not good. Please stick to the order. The questions are being asked, okay? So if it says question 1, go through the first one, then go through the second one, and go through the third one until you're done completely. However, you may have an issue with question number 2, for example, or question number 1. Am I going to be stuck in here not doing it? Just leave a space between them so that you can come back later on. So answer part 1 if you can. If you're not, go to part 2, question 2 in here, and answer it, and so on and so forth, and continue. Now, if for some reason you're stuck and you cannot continue, just leave enough space. There is plenty of time so that you can come back and insert your answer in there. In other words, stay organized. Keep the thing organized. Do not jump the steps. That is one way. This is not the only way, though. Okay, I can come in here instead and upload a file. If I upload a file, I can take a. If you have a webcam attached to your phone, probably you can do that. If you already have uploaded the file to Canvas, you can do that, or you can click and drag from your computer. So you can find your file, go to it, and drag it in here. So if you took a picture of your work with your phone, look at it on your phone. Can I read it? Can you read it? If you can read it, probably I can too. But if you cannot read it, I will not be able to read it. So make sure it's legible. Make sure you, after you take the picture, you can read it. Okay. If you can read it, then most likely I can. But the other way around is always terrible. If you cannot see it because the picture is fuzzy, too low resolution, or there is too much light hitting it so that it's too lit, or there is not enough light that it is completely dark, then in that situation, I will not be able to read it either. So make sure that it's legible. The other thing also is make sure your file is not a link to some picture somewhere else, okay? Check my, basically here, www.something.something, grab it from there. That's not acceptable. The reason why it's not acceptable is because it needs to be housed in the college repository, basically data storage of the college, so that it's graded and it stays there as part of the records for the college. So it cannot be stored somewhere else. Or Google Drive, and I have seen this more than anything else. People do a wonderful job apparently on their Google Drives, open Google Doc, do all kinds of answers, and then they come in here and they say, it asks them to bring it, so they drag it. Instead, they drag the link to their Google Drive. This has two problems. First of all, you really need to give me permission to get into your Google Drive, which I really don't want you to do, and I don't want you to share your Google Drive with anybody, okay? And the second problem is the same problem as I was talking about, in the sense that the file itself is stored somewhere else, not on the college property, which really needs to be there as part of your record. So it needs to be downloaded and uploaded in here so that it stays there permanently on campus. So there's a very important point in here when you're submitting your assignments. Please make sure you submit the actual file, not the link, okay? Or as I was doing earlier, you could just come in here and start answering. And you can combine both of them, okay? If you have an image to take, you can do that, or you can upload the text in here. Okay, makes sense? Yes, you can. You can do that too. David is asking, basically, can I just write it on a piece of paper by my hand? I don't have to do it on Word or anything else, and then upload the picture. That's fine too, as long as I can read it. Okay?
Professor, I have a question.
Yeah, yes.
So when I tried submitting two methods, a picture and a text entry, it only gave me the option to submit one. It didn't give me the availability to choose both.
Oh, I'm sorry. I have to check on that. So if that's the case, then I'm sorry. Probably it's true. Okay. Then maybe I have to retract what I said. Okay, because usually your experience is different than mine.
Yeah. Thank you.
Okay. So make sure then you do one or the other. Okay. But in any case, please do not give me a link to somewhere else where I cannot really grade it for you. And even if I do grade it, if you give me permissions, that's because basically we need it on Canvas. We need it on the college website. Okay, let me stop sharing. I really needed to make sure that this is clear. This is the purpose. One of the major points of today's thing is how to do these things all together. I know sometimes I tend to be very verbose and trying to explain things a little bit more in detail. And sometimes this kind of be repetitive and it might be boring for some people, but I want to make sure that it clarifies everything. There is no ifs or buts about it. Okay, so let me, and even then, I think there are questions that linger at the end that probably I don't go through them because either I forget or you guys don't ask, or and then later on we face an issue that we have to resolve. Anyway, so let me share with you the other assignment that I have started sharing with you, and that is this one in here. There is a mistake in here. This should not be 30 points. This again, it's not published, so by the time it's published, it's going to be fixed. This should be out of 20 points. Anyway, here is from Unit 10. Okay, and again, there is all kinds of things that need to be fixed. Not just, oh man, leave student view. So this is not March, okay? So I'll have to put the due date to fix the due date on it. So, and the points in here is not 30 points. I think it's 20 points. So there are things that needs to be fixed on this thing anyway. Okay. So the point being in here is that this is her unit 10, and you also will have a homework on it. And it tells you in here the smallest separation between Earth and Jupiter is 588 million kilometers. That's how far the moon is, I mean, the Jupiter is from the Earth in the least. Because remember, the Jupiter and the Earth, they orbit the sun. Granted, the Earth moves faster around the sun than Jupiter does. Jupiter takes about 12 years to go once around the sun, whereas the Earth would have gone 12 years. So the Earth is moving a lot faster. Why? Because it's closer to the sun. Okay. So at some point, they're closer to one another, and at some other point, the Earth will be on one side of the sun, and Jupiter will be on the other side, which puts it at around 968 million kilometers away from us. Okay. Obviously, Jupiter's size doesn't change. It's always about 440,000 kilometers. It's about 70,000 kilometers in radius, so diameter is about 140,000 kilometers. So the size doesn't change, but when we are very close from it, Jupiter looks bigger than when we are on the other side of the sun looking at Jupiter, Jupiter would look smaller. So that's the whole point of this exercise in here, is to find the sizes. Again, let me share, all of these problems have the same formula that they're going to be using. And I'm going to go through all of them first, and then we're going to give the formula in general. I'll probably give it on one of the examples. Suppose you are an alien living on a fictitious war-like planet, Myrmidon, or Myrmidon, I don't know how they say it. That's the war, what is it? The person who submits to the leader to go and do war and kill on his behalf or her behalf. And you want to measure its size. So what you do in this case, so you live on that planet, and you notice that the star is shining directly down a missile silo. So there is a missile silo, and the sun goes straight through it, about 1,000 kilometers from your hometown. On that town, whatever it's called, there is a silo, and silos, the sun goes straight through to them. That means there is zero shadow on that day. While at your location, the sun has a 36-degree straight overhead. So basically, the shadow is 36 degrees. So what is the circumference of that planet? And what is its radius? This is similar to how the method that was used actually by I lost the list. To find the size of the Earth and the radius of the Earth. Okay. A cloud directly above your head is 10 degrees across. Okay. So it's about 10 degrees across. Okay. In the sky. From the weather report, you know that the cloud is an altitude of 2,200 meters. How wide is the cloud? So you have the angular size, which is 10 degrees. And you know, if the cloud were to convert the entire sky 360 degrees, that is the circumference, which is just 2 pi times this number. And from there, you're going to find what that distance, except you don't have it in 2 pi, you have it in degrees. The ratio of the circumference in this case and the ratio of the distance in this case will be over the size will give you that 10 over 360. Okay, we're going to give the formula. It's the same formula for all of them, at least for the three of them. The Andromeda Galaxy M31 is in many ways similar to our own galaxy. The linear diameter of the Andromeda Galaxy is about 140,000 light years from side to side. Our galaxy is only about 100,000 light years. So Andromeda is a little bit bigger than our galaxy. But from our perspective, the Andromeda Galaxy is a maximum angular size of 3.18 degrees. How far away is Andromeda Galaxy? So if we know the angular size, if we know its physical size, then we should be able to find the radius. Okay, so let me give you the formula for 1, 2, and 3, and use it for either one of them to calculate, and you do the rest. And we will also talk about this one in here for this planet in here and how to find its size. So let me stop sharing. Let me share with you calculator, the OneNote. This is actually should be entitled in homework 2 and general homework, how to do homework problems too. So let me bring the pen and let me have the keyboard in here out of the way. So the formula that we have, remember, we have an object sitting at a distance, like Jupiter in this case. It has a physical size, I think we called it L, okay? And it's sustained by an angle, we called it alpha, and alpha better be in degrees, okay? If the distance between this object and this one is d, then in this case, 2 pi times d will give me the entire circumference. So L over 2 pi times d must be equal to the same ratio of this alpha in degrees over 360 degrees. From here, this is the formula we discussed in class. From here, I can find the distance, I can find the size. For the case of Jupiter, we need to have the angular size. We have everything except the angular size. So we need alpha actually, how big alpha is. So we need alpha. From this formula, if I multiply both sides by 360 degrees, this cancels that, and I will be left with only alpha in degrees. Then alpha in degrees for the case of Jupiter will be 360 degrees times how big Jupiter is. This is 140,000 kilometers divided by 2 pi, which is 6 point something, 6.28. this is just a number, times the distance to that object. Now the distance, we have two distances. We have when we are very close from the Jupiter, and that is actually the maximum angle because the distance is smaller. And then when we are further away from it, so we have, this is the situation for the case of Jupiter. Here is the sun. This is the Earth. And this is Jupiter. Today, 6 months later, the Earth is going to be here. 6 months later. Where is Jupiter? Jupiter barely moves in its orbit in 6 months. It doesn't really change much in its location. Okay, so the distance is really small in there. This distance in here is 588 million kilometers. This distance from here to here, when we are at furthest, is 900 and something. Let me check exactly how much was it. 968 million kilometers. 968 million kilometers. So the number that changes in here is D. When D is 968, the alpha will be small. So you have everything in this formula in here. You have 360. You have L, which is 140,000 kilometers. And you have the distance, 968 million kilometers and 588 million kilometers. You have to be careful in here. The distance is in kilometer and the size of Jupiter is in kilometer. Again, we have to be careful with the units. In this situation, we're lucky. We don't have to do anything. What we have to do is cancel them. In some other situations, we'll have to convert. Does this problem make sense to you guys? Yes, no, maybe. All we're trying to do is find the angular size, which is alpha in this formula that we have from the lecture. Given L and given the distance to Jupiter, two distances, when we are close by and when we are far away. So again, David is asking how big the size of Jupiter is, the angular size. When it's closer, it appears bigger. When it's further, when we are on 6 months later, it appears smaller. So we're trying to find that angular size. Make sense? So that's what we're trying to find. So that is what this alpha is. How big Jupiter would look like to you if you go out and look at it. And this is how big it's going to look like. Depends on how far away it is from us, of course. If it's close by, it looks bigger. But if it's far away, it's going to look smaller. Its actual size doesn't change. Jupiter is 140,000 kilometers in diameter. That's the end of it. But sometimes it's close by, and some other time is very far away. And some other times in between, it's somewhere in between. Make sense, this problem? Does it make sense or? Okay, beautiful. Very good. Okay, I'm glad that you guys are on top of this thing. So let me just look at the, so this is the formula we're going to be using for all three of these problems. Let me stop sharing and share and share. Okay, the cloud also the same thing. You're given alpha, which is 10 degrees, and you're given the distance d, which is 2,200. And in this case, you want to find L. So you need an L that makes this work. For the case of Andromeda Galaxy, you're given the size of Andromeda Galaxy, namely L, that is 140,000 light years. You're given the angle 3.18 degrees, and you're supposed to find D. So let me set up these problems quickly. Sure. Let me start with Andromeda because I remember the numbers for it. So again, for Andromeda Galaxy, we know that L, the size of Andromeda Galaxy, which is 140,000 light years, not kilometers, light years, divided by 2 pi times the distance. We don't know what the distance is. That's a question that we want to find, is how far Andromeda Galaxy is from us. This must be equal to the angle sustained, which is 3.18 degrees. They gave us this number, divided by 360 degrees. So we have to solve this equation for D. In other words, if I multiply by D in here and by D in here, this cancels this D from this D, and I'm left with a bunch of other things in here. So I'm going to multiply by 360 and divide it by 318. The reason why I want to do that is the 318 and the 318 cancel, and the 360 and the 360 cancel, and I will be left with D on this side. However, I need to do the same on the other side. In other words, I have to multiply by 360 and divide it by 318. So I'm left with 360 times L, because I didn't do anything to that number, divided by 3.18 times 2 pi. So in other words, the distance to Andromeda Galaxy will be 140,000 times 360 divided by 380.18 divided by 2 pi, but the answer is going to be in light years, because L is in light years. The degree of the 360 and the degree of 3.18 cancel. The 2 pi has no units, it's just 6.28, and L is in light years. So the answer is going to be in light years. Make sense? Does it make sense to you guys? So this is the formula that you're going to be ending up with, except the answer is going to be in light years. You take 360 times 140,000 divided by 318 divided by 2 pi. Yes, should I plug in the numbers? Yeah, the homework is just for you guys to help you understand the material more. So it's not really a challenge. It's not like an exam or anything like that. So it's not, that's the purpose of the homework, is to really help you be more confident about these numbers, what they mean. So let me share with you this thing in here. So we said 360 times 140,000 divided by, open parentheses, because everything is a denominator, so I have to be careful in here. First thing first, which is 3.18 degrees times 2 pi. 2 pi is 6.28. Close the parentheses, and now hit the equal sign. So it's giving me 2.52375 dot, which is a decimal point. Basically 2.5 million years, light years from here. So that's the answer. The answer to this question is basically the distance to Andromeda Galaxy is about 2.5 million light years from us. That's how the light that we're seeing right now from Andromeda Galaxy is left at 2.5 million years ago, before even modern humans basically walked out of Africa. So that's the whole point of it. Okay, only that happened what, about 100,000 years or something, 70,000 years or something. So it's not even within, I mean, it's much older than that. Okay, so this is one thing. So that's one light of Andromeda, basically, that we're looking at it tonight, how far the galaxy is. And this is actually our big closest neighbor to us in terms of galaxies. All of the other galaxies are further and further away. I mean, there are other galaxies that are nearby. Those are the satellite galaxies of our Milky Way, but they are not on their own. The only one that is on its own is Andromeda Galaxy, and it's that far. And there is other galaxies, actually about 50 of them in our local group. Anyway, let me go to the last one in here of this thing, which is the cloud thing, which is similar in a sense. They tell you the cloud is sustained by 10 degrees. So alpha is 10 degrees. And they tell you that the distance D is 2,200 kilometers. So how big the clouds are? Again, L, the cloud, divided by 2 pi times D. And D is 2,200 kilometers, is equal to alpha, which is 10 degrees, divided by 360. So all I have to do is multiply by 2 pi times D, both sides, 2 pi times D, and multiply by 2 pi times D. Because if I do that, this cancels. It gives me L, the size of the clouds, which is 10 over 360 times 2 pi. 2 pi is just 6.28 times the distance, which is 2,200 kilometers. So I'm going to leave that to you guys to finish it. And the answer is going to be in kilometers. Whatever the unit for L is going to be the answer to in this case. The unit earlier came out to be in light years because L was in light years. The distance now in kilometers, so it's going to give me the size of the clouds in kilometers. Let me answer the last one in here for that planet. So he was looking at the silo, and the silo has no shadow, and 1,000 kilometers away from him, the sun rays were making an angle of 36 degrees, okay? And they want to know how big the planet is, its circumference, and so on and so forth, okay? So remember from the experiment that we discussed in lecture, so the rays of the sun are coming straight to us in here. And because the Earth has this curvature, so the stick in here that is straight out will make that angle, will make that shadow, because the rays are hitting it at this angle. So basically that is how much the shadow is, 36 degrees in this case, which is the same angle as this one, which is actually this angle, 36 degrees. So the argument that we are making in here is 36 degrees divided by 360 degrees. This should be the same ratio as this arc distance, which is 10, divided by the entire distance, which is 2 pi times d, or 2 pi times r in this case, radius of the planet. It's the same thing. So this ratio is 1/10, and this is not a 10, this is 1,000. I'm sorry. This distance is 1,000 kilometers, okay? To be careful in here. So if I multiply both sides by 2 pi r to cancel this 2 pi r and 2 pi r on this side, and divide by 10 on this side and divide by 10 on the other side, I cancel the 10 and the 10, and I cancel this 10 with that 10. Actually, I'm sorry, I should have just multiplied it by r, not 2 pi r. I'm sorry. Should have just multiplied by r so that you cancel the r on both sides, and I will be left with, of course, an r in here. So r, the radius of that planet, should be 1,000 divided by 10, which is just 100, divided by 2 pi. That's it. Did I say ratio is 10 in this case? What am I saying in here? I'm sorry, it's 1/10. This is incorrect. Okay. Apologies, I made a mistake in here. Let me fix this. Ignore that, okay? So we said again, it's 36 degrees, still correct, divided by 360 degrees. Must be equal to, again, 1,000 kilometers. That is that distance between the silo and where he is at, okay? Divided by 2 pi times the radius of the planet. This ratio is not 10, it's 1/10. I'm sorry. 36 divided by 360, I made a mistake. I said it's 10, and that is not correct. It should be a 10th. Okay. Now we can multiply both by r and both sides by r. If we do that, this r cancels. Then I also have to multiply by 10, both sides. The reason why I want to do that is I want to get rid of this 10. So R is isolated by itself. Then the answer is going to be, R is going to be 1,000 times 10, which is 10,000 actually, divided by 2 pi, or 10,000 divided by 6.28. And that is also the units of that distance, which is kilometers. So the answer is going to be in kilometers. So the answer is 10,000 divided by 6.28, which puts it around 1 point something, slightly bigger than the moon, probably, or around the size of the moon, something like that. Okay. Okay, let me check quickly with the calculator because I'm curious about this number in here. 10,000 divided by 6.28. It's 1.9, 1.5 or 1,592 kilometers. Okay, and that's smaller than the moon. Actually, remember the moon's diameter is about, the moon's radius is about 1,700. So this planet is less than the moon. Okay, in other words, if you were on the moon, you're going to see something exaggerated like this one, because remember, in our case, for the case of the Earth, the guy saw like 7 degrees only for the shadow in Alexandria versus Cyan, which has no shadow. And that distance was quite a bit of distance. And in this case, the angle is 36 degrees, is much larger. Okay. I wanted the guys to get you started on homework because I want to make sure that you guys are on top of this materials, you understand them. And because I truly believe in the power of the homework to making you guys much more at ease with the content. Because once you get into the habit of doing them, and once you get into understanding how they work, you really are going to gain a lot from them. They are not going to be part of any test. The only way that you're going to be tested on this kind of calculations is through the homework, and that's it. So make sure you take full advantage of them because I believe that you're going to benefit a lot from them. Okay. Sounds good, guys? Okay, very good. Thank you, Kiara. Okay. I see you guys. We have a lab in here, so I'm going to stop the recording. So I'm actually in the lab room today. So I'm going to be hanging around, and I will see you guys later on. For those who are sitting in the lab, those who are not in the lab, I'll see you next week. Have a safe and nice weekend for the guys who are not going to be in the lab, and enjoy your holiday, and I will see you next week.